Vibration subtopic. This is compulsory for you will get 4 marks in gate. Either two marks questions or one 2 mark question and two 1 mark questions. So let's go through it. The repetitive oscillatory motion of a system about some mean equilibrium position is known as vibrations. Classification of vibrations. On basis of excitation, vibrations free or natural vibrations 2 marks, forced vibrations 2 marks, parametrically excited vibrations and self-excited vibrations. Free or natural vibration, like in interview they may ask what is free or natural vibrations and what is forced vibration. Free or natural vibration, if a system is disturbed from its initial equilibrium by some force or couple, and then disturbing force or couple is removed and the system is left to oscillate by its own, these vibrations are known as free vibrations. Example: pendulum of a clock, motion of a child on a swing after an initial push. Here force or couple will be there, but it won't continue to be in effect. But in forced vibration, if the reason behind the motion is present continuously, the oscillation of system is known as forced vibration. Example: vibration of IC engine, electric motor, centrifugal pump. Forced vibration. External excitation force due to unbalanced rotating and reciprocating inertia forces. Base excitation or support motion. On basis of direction of motion, vibrations: longitudinal vibrations, transverse vibration, torsional vibration. Here system rod plus rotor. Longitudinal vibration, so it will vibrate longitudinally. If the rotor moves in longitudinal direction of rod, the vibration of system are known as longitudinal vibrations. As a result of it, the system will be subjected to direct tensile and compressive stresses alternatively. This will be tensile and this will be compressive. Transverse shear load: if the rotor moves in direction almost perpendicular to the longitudinal axis of the rod of the oscillations are known as transverse vibrations. As a result of it, the system will be subjected to alternate bending stresses. Torsional vibrations: if rotor oscillates about longitudinal axis of rod, oscillations are known as torsional vibrations. As a result of it, the system will be subjected to alternate torsional shear stress. On basis of degrees of freedom, this is another classification. Degrees of freedom is defined as a minimum number of independent displacement variable required to design the motion of the system. Vibrations: single degree of freedom, multi degrees of freedom, infinite degrees of freedom. Spring flexible element: degree only x direction is there, degree of freedom is equal to 1. Spring on rigid rod, x1 is equal to x2, the degree of freedom is equal to 1. And here if it is rigid rod, here two springs, k1 k2 m1 m2, x1 not equal to x2, so degrees of freedom is equal to 2. This thing, a simple pendulum, only theta, degree of freedom is equal to 1. String, both are strings, theta 1 not equal to theta 2, degree of freedom is equal to 2. Rod, then degree of freedom is equal to 1. One spring, two masses connected, x1 x2, x1 not equal to x2, so degree of freedom 2. String connected, x1 is equal to x2, degree of freedom is equal to 1. And this is x, this is theta, x not equal to theta, so degree of freedom is equal to 2. X theta, x equal to r theta, so degree of freedom 1. And W, rigid cantilever beam, degree of freedom is equal to 0. W, flexible cantilever beam on transmission wire or cable, degree of freedom is equal to infinity. M1 M2 M3, so Y1 Y2 Y3 different deflections will be there. Here XA not equal to XB not equal to XC, so degree of freedom is equal to 3. This theta will have some relation, but x1, x2, xa, xb, xc won't be having any relation. System parameters. Any oscillating system is having following three parameters: inertia, restoration, damping. Inertia property or ability. Inertia it is property of a system due to which it resists any change in its state, either of the rest or motion. Translation measure of inertia, mass, rotation, distribution of mass about axis of rotation, second moment of mass about axis of rotation, mass moment of inertia about axis of rotation, force, external agent, change in position or shape, change in position, engineering mechanics, inertia, mass, second moment of inertia, shape, form, geometry along with mass, area or second moment of area. Any arbitrary point pivotal and oscillates. Let m is equal to mass of compounded pendulum. ICM is always IXX is equal to question mark. IXX greater than ICM always. IXX is equal to ICM plus MH into H. IXX is equal to ICM plus MH square. We already know that. Compound pendulum HM. Okay, H is at center of mass where M can be placed. K is equal to radius of gyration about center of mass. ICM actual is equal to ICM due to lamina. ICM is equal to MK square. IXX is equal to ICM plus MH square. IXX is equal to MK square plus M of K square plus H square. Ring ICM is equal to MR square. ICM is equal to MK square. Then K is equal to R about center of mass. Disk ICM is equal to MR square by 2. ICM is equal to MK square. K is equal to R by root 2 about center of mass. Disk is in pure rolling. IP is equal to ICM plus MR square is equal to MR square by 2 plus MR square. IP is equal to 3 by 2 MR square. If IP is equal to MK square, radius of gyration about I center, K is equal to R root of 3 by 2. Fi is equal to mx double dot in a translation. Ti is equal to I theta double dot in rotation. What will be force required to accelerate a disk of mass m which is rolling without slipping on horizontal plane, having acceleration a and radius r and radius of gyration about center of mass as k? Then m into k square, what force required to accelerate? Then I is equal to mk square, t is equal to I alpha, f is equal to uh, I alpha by r. F is equal to I alpha by r. F at answer, and then F is equal to A is equal to R alpha. F is equal to MA plus I alpha by R is equal to MA plus I into MA square by R square. MA into MA plus MK square A by R square. F is equal to MA into 1 plus K square by R square. Pinion with radius R1 and inertia I1 is driving gear with radius R2 and inertia I2. Torque tau1 is applied on the pinion. Following are free body diagram of pinion and gear. Which of the following relation is true? Okay, this is like previous gate question. F1, F2. F1 is equal to F2 as they both will be in contact. Both will be in contact. Tau1 is equal to this is the possible thing. Tau1 is equal to I1 plus I2 into R1 by R2 whole square into theta 1 double dot. F2 is equal to I2 into R1 theta 1 double dot by R2 square. Okay. Restoration. If a system is in equilibrium equation, then it will always return to the initial equilibrium position by its own. Whenever disturbed from there, the property due to which system returns is known as restoration. Modeling or restoration or representation. Springs linear or torsional. Gravitational restoration, weight of body. Fluid buoyancy force. Restoring force acts Fs. Equilibrium position L sin theta. Restoring force is equal to mg L sin theta. Mg L sin theta. Restoring couple is mg L sin theta. Here, if it is changed, the restoring couple is equal to mg capital R minus small r into sin theta. Uh, Fluid restoring force is equal to weight of column of 2x length. If x is down, x is up, total 2x, rho a 2xg. X here x will be displaced and length of column whose weight will be restoring force is equal to x plus x sin theta. X sin theta horizontally. And F restoration is equal to F buoyancy is equal to WAX W specific gravity specific weight. Linear spring KFS Hooke's law Fs directly proportional to minus x. Negative sign indicate that spring force will be opposite in the direction of displacement. Fs is equal to kx, k is equal to Fs by x. Unit of k is Newton per mm. Spring stiffness or spring rate or spring constant. If x equal to 1 unit, k is equal to Fs is equal to F. So spring stiffness is amount of restoration force required to produce unit deflection in spring. K is equal to g small d power 4 by 8 capital D cube n, or g small d power 4 by 64 capital R cube n. Capital R small mean of coil radius, small d wide diameter, modulus g capital E is modulus of rigidity. K inversely proportional to n, or nk is equal to constant. Number of turns is equal to length of spring. K inversely proportional to length of spring. If spring of length is divided and cut into 2, then L by 2 L by 2 K will be 2K 2K. K cut into parts of x and y. Lk is equal to xk dash. K dash is equal to Lk by x. K double dash is equal to Lk by y. Spring connection of springs K1 K2 K equivalent when both are connected. K equivalent is equal to K1 K1 K2 by K1 plus K2. Condition for series combination: deflection of spring 1 plus deflection of spring 2 is equal to deflection of mass. Delta S1 plus delta S2 is equal to delta mass. F force in spring 1 is equal to force in spring 2 is equal to mg. Fs1 is equal to Fs2 is equal to mg. 1 by k equivalent is equal to 1 by k1 plus 1 by k2. Parallel k1 k2 k equivalent is equal to k1 plus k2. If mass remains horizontal, so deflection of spring 1 is equal to deflection of spring 2 is equal to deflection of mass. Delta S1 is equal to delta S2 is equal to delta mass. Force in spring 1 plus force in spring 2 is equal to mg. K equivalent is equal to k1 plus k2. Here, as if axis displacement, both will be in same direction. So K equivalent is equal to K1 plus K2. Delta S1 is equal to X. Delta S2 is equal to X. Displacement of spring 1 delta S1 is equal to X. Displacement of spring 2 delta S2 is equal to X minus Y. This floor is vibrating with Y is equal to Y sin omega t. Fs1 is equal to K delta S1 is equal to Kx. Fs2 is equal to K2 delta S2 is equal to K2 into X minus Y. Neither series nor parallel. Delta S1 not equal to delta S2, Fs1 not equal to Fs2. Parallel combination, if it is like this, delta Fs1 or F delta 1, mgl is equal to Fs1 into A. into a fs1 is equal to mgl by a. Superposition, when using superposition theorem, we can replace one spring by one string. Okay, delta s1 is equal to fs1 by k is equal to mg by k1 into l by a. Delta from similar triangles, delta 1 by l is equal to delta s1 by a. Delta 1 is equal to mg by k1 into l by a whole square. If one is replaced by string and other by delta, then other by spring, then fs is equal to mg. Delta 2 is equal to delta s2 is equal to mg by k2. Delta mass net is equal to delta 1 plus delta 2. Delta mass net is equal to mg by k1 into l by a whole square plus mg by k2. Omega n is equal to root of g by delta mass. K1 K2 R theta is equal to delta S1 is equal to Fs1 by K1 is equal to 2 mg by K1. Fs1 is equal to 2 mg. Delta 1 is equal to 2 delta S1. Delta 1 is equal to 4 mg by K1. Fs2 is equal to mg. Delta S2 is equal to mg by K2. Delta 2 is equal to mg by K2. And delta net is equal to delta 1 is equal to mg by k1. 1 is replaced by string. Delta 2 is equal to this is k2 to r. Delta 2 by r is equal to mg by 2k by 2 l. Delta 2 is equal to mg by 2k2 into 1 by 2r into r. Delta 2 is equal to mg by 4k2. Mg by 4k2. Delta directly proportional to epsilon Hooke's law up to proportional to limit sigma is equal to E epsilon. F directly proportional to minus x Hooke's law. And P is equal to AE by L into delta L. F is equal to Fs is equal to Kx. K is equal to AE by L. Type of loading axial geometric property A x cross section material property E rigidity is equal to G into M. Axial rigidity is equal to A. Stiffness is equal to rigidity by length. Axial stiffness is equal to AE by L unit Newton per meter. Flexural or bending Ix geometric property G Ixx or Iyy. Material property E. Flexural rigidity is equal to EA. Flexural stiffness is equal to F of EI by L. Torsion IZZ or J. G material property. Torsional rigidity GJ. Torsional stiffness is equal to GJ by L is equal to T by theta. Flexural stiffness depends upon type of beam and loading and type of loading. Parallel connection will increase combined stiffness. Therefore, it is preferred in machines automobile. Damping, it is responsible for the loss of energy. It is the property due to which a system resists the relative motion. Damping, modeling or reason or reciprocal representational damping, frictional damping or column damping, material damping or hysteresis, even viscous damping. I think we will discuss about viscous damping more here. In frictional viscous damping is in fluids. In frictional damping, a constant frictional force always acts opposite to the direction of relative motion. In viscous damping, fluid having appreciable viscosity is used to obtain the loss of energy. Dashpot or damper. Work done by force is equal to loss of energy is equal to Fx x piston displacement. As a point of horizontal cylinder which is not moving, no slip condition, y1 is equal to 0. And Newton's law of viscosity, tau is equal to mu du by dy is equal to mu into u2 minus u1 by y2 minus y1. Tau is equal to mu into u2 minus 0 by y2 minus 0. Tau is equal to mu u2 by y2. Shear stress directly proportional to velocity of fluid, shear force directly proportional to velocity of fluid, drag force directly proportional to velocity of fluid, damping force directly proportional to velocity of fluid. Ft directly proportional to x dot, Ft is equal to cx dot, c is equal to Ft by x dot, c damping coefficient, unit of c Newton second per meter. Inertia translation, Fi directly proportional to x double dot, Fi is equal to mx double dot. Rotation, Ti directly proportional to theta double dot, Ti is equal to I theta double dot. Restoration, Fs directly proportional to x, Fx is equal to kx. Ts directly proportional to theta, Ts is equal to kt into theta. Kt torsional stiffness Newton meter per radian. Damping, Fd directly proportional to x dot, Fd is equal to cx dot. Td directly proportional to theta dot, Td is equal to c theta, c equivalent theta dot Newton meter second per radians. If a system is in vibration, its kinetic energy will be converted into potential energy and vice versa. The conversion of energy can take place either with or without loss of energy. Inertia deals with Ke. Translational K is equal to half mx dot square. Rotational Ke is equal to half I theta dot square. Restoration deals with potential energy mgh on spring energy of spring is equal to half kx square. Damping deals with loss of energy. Lumping of parameters. Lumping of parameters. So this I guess lumped model x1, x2, x3. If it is like this, then it is called lumped model. Flexible cantilever beam of mass degree of freedom is equal to infinity. Damping is present. The analysis of single degree of freedom mass spring damper analysis of single degree of freedom undamped longitudinal free vibrations. Damping is undamped, so damping is absent, there is no loss of energy, total energy of system is equal to constant, amplitude of oscillation is equal to constant, reason behind the motion will be removed after providing initial displacement free vibration. Methods. Newton's method or D'Alembert's principle, sigma F external is equal to Fi in translation, sigma T external is equal to Ti in rotation. D'Alembert's principle, dynamic equilibrium, sigma F external is minus of minus Fi is equal to 0, sigma T external minus of minus Ti is equal to 0. Energy method, d by dt of total energy of system is equal to 0. ALS method, maximum kinetic energy of system is equal to maximum potential energy of system. Energy extreme position, equilibrium position, P max, K max. In free vibration, amplitude of vibration is always very small. We can use following result, limit theta tends to 0, sin theta is equal to theta, theta tends to 0, cos theta is equal to 1, theta tends to 0, 1 minus sin cos theta is equal to theta square by 2. By applying sin square theta by 2, sin square theta by 2, we will get theta square by 2. Steps to apply Newton's method or D'Alembert's principle. Step 1. Recognize the system. Inertia restoration. Step 2. Identify the displacement variable, either x or theta or both. Step 3. Provide some displacement to the system by ourselves and draw the free body diagram at displaced position. Step 4. Write the equation of motion. Let mass of spring is negligible. System is equal to spring plus mass. Case 1. K M mass M X Fi Fs will be in this direction, N Mg equilibrium position, X displacement will be like this. D'Alembert's principle, sigma Fx is equal to 0, Fi plus Fs is equal to 0, Mx double dot plus Kx is equal to 0, X M d square x by dt square plus Kx is equal to 0. Second order differential equation, x double dot plus k by m x is equal to 0, x double dot plus omega n square x is equal to 0, where omega n is equal to root k by m. Case 2. Case 2, unstretched length of spring or free length. Delta st k m k delta st mg fi fs mg. Inertia delta st is equal to static deflection due to mg. Delta st is equal to constant at equilibrium position. System will be in rest. K delta st is equal to mg. K by m is equal to g by delta st. D'Alembert principle. Sigma fx is equal to 0, fi plus fs is equal to mg, mx double dot plus k into x plus delta static. X plus delta static is equal to mg, mx double dot plus kx plus k delta static is equal to mg. Initially itself, when mass is placed, delta st will be there. K delta st and mg will be initially balanced. So, okay. So, final equation will remain same. Mx double dot plus kx is equal to 0. X double dot plus omega n square x is equal to 0, where omega n is equal to root k by m is equal to root g by delta st due to weight delta st changes. If unstretched length of spring changes due to mg, then mg will not appear in the equation of motion. When mg is not present, if p is equal to 0. The unstretched length of spring changes due to mg, then mg will not appear in equation of motion. When mg is not present, that is p is equal to 0. Alternate approach D'Alembert principle, fi plus fs is equal to 0, mx double dot plus kx is equal to 0. FBD according to Newton's method, equation of motion, fs fi downward, fi is equal to fs, mx double dot is equal to kx, x double dot is equal to omega n square k, omega n square x. Case 3, on an inclined plane. On an inclined plane, length delta st will be initially balanced at equilibrium position. System is in rest. K delta st is equal to mg sin alpha. K by m is equal to g sin alpha by delta st. D'Alembert principle. Sigma fx is equal to 0. Fi plus fs is equal to mg sin alpha. mx double dot plus k into x plus delta static is equal to mg sin alpha. Mx double dot plus kx plus k delta static is equal to mg sin alpha. Mx double dot, these both will cancel out. Finally, mx double dot plus kx is equal to 0. X double dot plus omega n square x is equal to 0, where omega n is equal to root k by m is equal to root g sin alpha by delta st. Root g sin alpha by delta st. Alpha and delta st depends on each other. Alternative approach, take x in this direction itself, then it will be easy to write. Fi plus fs is equal to 0, mx double dot plus kx is equal to 0. Case 4, k theta x phi kx cos theta, this is cos theta, okay. D'Alembert principle, fi plus kxc cos theta is equal to 0. Mx kxs cos theta. X, this is different, and axis spring displacement is different. Mx double dot plus k of x cos theta into cos theta is equal to 0. Mx double dot plus k cos square theta into x is equal to 0. Mx double dot plus k cos square theta into x is equivalent to mx double dot plus k dash into x. Mx double dot plus k cos square theta into x is equal to 0. Replace the springs. Okay, we can replace like this, k cos square theta. Replace springs which are not in direction of displacement, that is k1 and k2. X is in this direction, So k2 cos square alpha, this one we can verify the k1 cos square of 90 minus alpha, and we can write in that direction itself. Mx double dot plus k equivalent x is equal to 0. Mx double dot into k1 sin square alpha plus k2 sin square k2 cos square alpha plus k3 into x is equal to 0. Case 5, when mass of spring is given, let gamma is mass of spring per unit length. Ms is equal to gamma into L. Mass of element dm is equal to gamma dy. Velocity of element v element by x dot is equal to y by L. V element is equal to x dot y by L. X dot y by L. Total energy of system mass plus spring is equal to total energy of mass plus total energy of spring. Ke of mass half m dot x square, or half m x dot square, or half I theta dot square. Potential energy of mass mgh, which will appear when mg will appear in equation of motion, that is when mg does not provide delta st. Spring energy of system half kx square. Always spring kinetic energy of spring will appear only when mass of spring is given. When mass of spring is given, gamma d v element is equal to x dot y by L. Ke of element dk is equal to half dm v element square. Ke of spring is equal to integral 0 to L dke is equal to 0 to L half gamma dy x dot y by L whole square is equal to half gamma x square by L square integral 0 to L y square dy. Ke of spring is equal to half gamma x dot by L square y cube by 3 0 to L is equal to half gamma x dot square by L square L cube by 3 is equal to 1 by 6 gamma L into x dot square. Finally, kinetic energy of spring is equal to 1 by 6 ms x dot square. 1 by 6 ms x dot square. Energy methods. D by dt of total energy of system is equal to 0. D by dt of Ke of mass plus Ke of spring plus spring energy of spring is equal to 0. D by dt of half mx dot square plus 1 by 6 ms x dot square plus half mx half kx square is equal to 0. Half m 2x dot x double dot plus 1 by 6 ms 2x dot x double dot plus 1 half 2 half k 2x x dot is equal to 0. Taking x dot common, mx double dot plus ms by 3 x double dot plus kx is equal to 0. M plus ms by 3 into x double dot plus kx is equal to 0. X double dot plus k by m plus ms by 3 into x is equal to 0. X double dot plus omega n square x is equal to 0. Omega n is equal to root of k by m plus ms by 3. Solution of equation of motion x double dot plus omega n square x is equal to 0. D square plus omega n square x d square x double dot plus omega n square d square x plus omega n square x is equal to 0, where capital D is equal to d by dt d square plus omega n square into x is equal to 0. X is equal to f of t. X is equal to cf plus pa. Pa 0. Cf d square plus omega n square is equal to 0. D square is equal to minus omega n square. D is equal to plus or minus I omega n. X is equal to a cos omega n t plus b sin omega n t. Displacement equation. A and b are constant whose values depends on boundary conditions. Let x a is equal to x sin pi, b is equal to x cos pi, x is equal to root of a square plus b square, tan pi is equal to a by b, x is equal to x sin omega n t plus pi. Displacement equation. Conclusions of from displacement equation, x is equal to capital X sin of omega n t plus pi. Phase lag. Presence of sinusoidal term indicates the displacement is in harmonic nature. Frequency of oscillation angular omega n radian per second. Linear fn is equal to omega n by 2 pi. Natural linear frequency is unit second inverse or h, defined as number of cycles per second. Time period of oscillation t is equal to 2 pi by omega n is equal to 1 by fn units second. It is defined as time required to complete one cycle. Amplitude of oscillation, it is defined as the maximum displacement of system from the mean position. X max is equal to capital X is equal to X max maximum displacement of or amplitude. Analogy between translation and rotation. Translation, displacement x theta, velocity x dot theta dot, acceleration x double dot theta double dot, inertia m, and rotation I equivalent about axis of rotation. Equation of motion mx double dot plus kx is equal to 0, x double dot plus omega n square x is equal to 0, I equivalent theta double dot plus k equivalent theta is equal to 0, theta double dot plus omega n square theta is equal to 0. Natural angular frequency omega n is equal to root k by n. Here omega n is equal to root k equivalent by I equivalent. X is equal to capital X sin omega n t plus phi. Theta is equal to theta naught omega n t plus phi. X max is equal to capital X. Theta max is equal to theta naught. Displacement equation. Velocity equation x dot is equal to x omega n cos omega n t plus phi. X dot max is equal to x omega n. Theta dot is equal to theta naught omega n cos omega n t plus phi. Theta max is equal to theta dot max is equal to theta naught omega n. Acceleration equation x double dot is equal to minus x omega n square sin omega n t plus phi. X double dot max is equal to plus x omega n square. Theta double dot is equal to theta naught omega n square sin of omega n t plus phi. Theta double dot max is equal to theta naught omega n square. Rotating vector x is equal to capital X sin of omega n t plus phi. Sin at reference axis if cos reference is ordinate. X double dot is equal to x sin omega n of abscissa means this, ordinate means this. Sin omega n sin of omega n t plus pi by 2. X double dot is equal to x capital X omega n square sin of omega n t plus pi. X is equal to a cos omega n t plus b sin omega n t. X sin pi t is equal to 2 pi by omega n. Small x is equal to capital X sin of omega n t plus pi. At t is equal to 0, x is equal to capital X sin pi. X max is equal to x. Note, natural frequency omega n of oscillation is free from boundary conditions. In SHM, the acceleration leads to velocity by 9 leads to the velocity by 90 degrees, and velocity leads to the displacement by 90 degrees. In SHM, the acceleration leads to the displacement by 180 degrees. Shifting of ring parallel to its position. At a distance a, K1 is there, L mass is there. Fs1 is equal to mg L by a. Delta S1 is equal to mg by K1 into L by a. Delta mass delta mass is equal to mg by K dash. Delta mass 1 is equal to delta S1 into L by a. Mg by K1 is equal to mg by K1 into L by a square. K dash is equal to K into A by L square. A by L whole square. This is a workbook question. And this is just simple one. D'Alembert principle, taking moment about P. Let clockwise couples are positive. IP theta double dot plus some mgl sin theta is equal to 0. IP theta double dot plus mgl theta is equal to 0. Theta double dot plus mgl by IP into theta is equal to 0. Equation of motion. Theta double dot plus omega n square theta is grounding equal to 0. Grounding equation. Omega n is equal to root of mgl by ip. Ip is equal to ml square. Omega n is equal to root g by l. Natural frequency of simple pendulum is independent of from mass. T is equal to 2 pi by omega n is equal to 2 pi root l by g. System is equal to compound pendulum. D'Alembert principle, taking moment about point P. Let clockwise couples are positive. IP is IP theta double dot plus mga sin theta is equal to 0. IP theta double dot plus mga theta is equal to 0. K is equal to radius of gyration. Theta double dot plus mga by ip into theta is equal to 0. Equation of motion. Theta double dot plus omega n square into theta is equal to 0. Grounding equation. Omega n is equal to root mga by ip. Ip is equal to mk square plus ma square is equal to m into k square plus a square. Omega n is equal to root of mga by m into k square plus a square. Omega n is equal to root ga by k square plus a square. Equivalent length of simple pendulum which results in same frequency. L equivalent is equal to k square plus a square by a. Okay. Okay. These are all good questions. Rayleigh's method, maximum Ke of system is equal to maximum Pe of system. Maximum Ke of cylinder is equal to maximum C of springs 1 and 2. Half Ip theta dot square is equal to half Kt xs square plus half Kt xs max square. Ip theta dot max square is equal to 2K r plus a whole square into theta max square. Ip theta naught omega n whole square is equal to 2K r plus a whole square into theta naught. Omega n into omega n is equal to root of 2k into r plus a whole square by ip. Translational energy d by dt of half I m x dot c m square plus half c I c m theta dot square is equal plus 2 into half k x square is equal to 0. Omega n is equal to finally omega c ICM is half mr square. Omega cm is equal to root of k r plus a whole square into 4 by 3 mr square. Okay, these are the simple questions. G method, d by dt, Rayleigh method, okay. Okay, now analysis of single degree of freedom, damped or free vibration. Damping is present, energy loss will occur, amplitude of oscillation or displacement of system will decay with respect to time. Disturbing force or couple will be removed after providing initial displacement. System is equivalent to spring plus mass plus damper. Mx double dot plus Cx dot plus Kx is equal to 0. X double dot plus C by Mx dot plus K by Mx is equal to 0. X double dot plus C by M x dot plus omega n square x is equal to 0. D square x plus C by M into dx plus omega n square is equal to 0. Equation of motion, D'Alembert principle, Fi plus Fd plus Fs is equal to 0, where capital D is equal to d by dt d square plus C by M d plus omega n square x is equal to 0. Solution, x is equal to f of t, x is equal to Cf plus Pa is 0 in this case. Cf d square plus C by M d plus omega n square is equal to 0. D 1 comma 2 is equal to minus C by M plus or minus root of C by M whole square minus 4 omega n square. D 1 comma 2 is equal to minus C by 2M plus or minus root of C by 2M whole square minus omega n square. Damping factor epsilon is equal to root of C by 2M whole square by omega n square is equal to C by 2M omega n. Epsilon omega n is equal to root k by m. Epsilon is equal to 2 C by 2M omega n is equal to C by 2 root mk. D 1 comma 2 is equal to minus epsilon omega n plus or minus root of epsilon omega n whole square minus omega n square. D 1 comma 2 is equal to minus epsilon omega n plus or minus omega n into root of epsilon square minus 1. Vibratory system on basis of amount of damping present on the system. Undamped system, epsilon is equal to 0, that is damping is option. In case of damped system, epsilon greater than 0, epsilon less than 1, underdamped, epsilon equal to 1, critically damped, epsilon greater than 1, overly damped. Case 1, underdamped, epsilon less than 1. D1 comma 2 is equal to minus 1 epsilon omega n plus or minus omega n into root of minus 1 into 1 minus epsilon square is equal to minus epsilon omega n plus or minus I omega n root of 1 minus epsilon square. Let omega n into root of 1 minus epsilon square is equal to omega d. So D1 comma 2 is equal to minus epsilon omega n plus or minus I omega d. Cf is equal to x is equal to e power minus epsilon omega n t into a cos omega dt plus b sin omega dt. Here a and b are constant whose values depend on boundary condition. X is equal to a x sin pi, b is equal to x cos phi. Then x is equal to capital X e power minus epsilon omega nt into sin of omega dt plus pi. Displacement equation. Conclusion. From displacement equation, Displacement is harmonic in nature. Frequency of oscillation is equal to omega d, damped natural frequency. Omega d is equal to omega n into root of 1 minus epsilon square. Omega d by omega n whole square plus epsilon square is equal to 1, equation of circle. Omega d by omega n epsilon, then a circle will come. For I 0 less than epsilon less than 1, omega d by omega n less than 1, omega d less than omega n. Damped natural frequency is less than undamped natural frequency. Damped time period Td is equal to 2 pi by omega d, 2 pi by omega d greater than 2 pi by omega n. Damped time period greater than undamped time period. Amplitude of oscillation will decay exponentially with respect to time is equal to x e power minus epsilon omega n t. Is a function of f of e power minus t. Equation of is equal to x e power minus epsilon omega n t. Td, it will decrease. Okay. Ratio of successive amplitudes x0 by x1 is equal to x1 by x2 is equal to x2 by x3 so on is equal to xn minus 1 by xn is equal to constant is equal to e power delta t, where delta is equal to 2 pi epsilon by root of 1 minus epsilon square, or epsilon is equal to delta by 4 root of 4 pi square plus delta square. X0 by x1 is equal to x1 by x2, x1 square is equal to x0 x2. The successive amplitudes are in geometric progression. Logarithmic decrement x0 by x1 is equal to x0 by x1 into x1 by x2 so on xn minus 1 by xn is equal to e power delta into e power delta so on e power delta. X0 by xn is equal to e power n delta. N delta is equal to ln of x0 by xn. Delta is equal to 1 by n ln of x0 by xn. Case 2, epsilon is equal to 1, critically damped system. Epsilon is equal to c by 2m omega n. 1 is equal to cc by 2m omega n. Cc is equal to 2m omega n is equal to 2 root km, where cc is critical damping coefficient. Epsilon is equal to c actual by cc. C epsilon is equal to actual damping constant by critical damping coefficient. The epsilon is damping ratio or damping factor. C is damping coefficient. D1 comma 2 is equal to minus epsilon omega n plus or minus omega n into root of epsilon square minus 1. If epsilon is equal to 1, D1 comma 2 is minus omega n. Cf is equal to x is equal to a plus bt e power minus omega n t. Displacement equation. Conclusion of displacement equation. Displacement will decay exponentially with respect to time. Displacement is a periodic in nature. In nature will not oscillate. It will be like this. Epsilon equal to 1 will be like this. Epsilon greater than 1 is like this. Epsilon less than 1 it will oscillate. AK47 epsilon equal to 1, critically damped. Critically damped. Oscillation will not be there, and that is motion will be aperiodic. Case of critically damped as well as over damped, but critically damped is defined as smallest amplitude smallest amplitude of damping for which there will be no oscillation in free vibration. In army, ease of operation is most important. 100% success rate, 100% reliability. Analogy between translation and rotation. Equation of motion mx double dot plus cx dot plus kx is equal to 0. I equivalent theta double dot plus c equivalent theta dot plus k equivalent theta is equal to 0. Epsilon is equal to c by 2m omega n. Epsilon is equal to c by 2 root km. Omega n is equal to root k by m. Epsilon is equal to c equivalent by 2 I equivalent into omega n. Epsilon is equal to c equivalent by 2 root k equivalent into I equivalent. Omega n is equal to root of k equivalent by I equivalent. Example from workbook. Okay.